Hey, this is lesson 14-2, trigonometry. We're going to learn how to find missing side lengths in right triangles today. But before we get started on that, we're going to need a calculator today, and we're going to make sure the calculator is set up properly. You know, there's lots of different settings in calculators, most of which you haven't played with and don't even know exist. But there's a button in the upper left-hand corner of your graphing calculator if you're carrying a TI 81234, whatever. It's called mode. And if you press that mode button and you arrow down to the third row, and then you'll see these two options of different ways of measuring angles. You've probably never heard of radians, and that's okay. But you want, anytime you type in a number that's supposed to represent an angle, you want the calculator to interpret that angle measure as a degree angle measure. And so you need to arrow over until degrees is highlighted and then hit the enter button, press the enter button to save that setting. And then you can quit out of that mode screen by, you want to press the second and then find the quit option, which is also near the top of your calculator keypad to get out of that screen. So you got to have it set to degrees. Here's a little video in case that went a little fast for you. It's about a minute and a half video that shows you somebody pressing the buttons to get this done. If you're carrying a less expensive calculator, maybe not a graphing calculator, that's fine. But even if you're carrying an inexpensive calculator, you probably also need to make sure that your calculator is set to degree mode. Now, in the window of your calculator, there probably is a little three-letter abbreviation telling you what mode your calculator's in. It might say DEG, it might say RAD for radians, and it might say GRA for this other way of measuring angles. But how do you change that if it doesn't say DEG? There's probably a DRG button on that calculator, and if you just press that, then the setting will cycle through degrees, radians, and gradians, and you can just keep pressing that button until you see the DEG show up, and then it's in degree mode. And then if you want to test, if you really got it set up properly and you saved the setting properly, put in tangent, find the tangent button. Okay, there's a tangent button on your calculator. Find that button. Now, don't get confused. There's a tangent button, and somewhere nearby the tangent button, I'm not sure if it's, I got to look. I haven't held a calculator in so long now. Sine, cosine, tangent. Yes, right above the tangent button. Again, if you're carrying a TI 80 something or other, right above the button that says tangent, it says tangent, and it looks like tangent to the negative first power. That's a different thing, okay? You just press the tangent button so that you get tangent showing up in your window, and then put in 45 degrees. You don't need a degree symbol. The calculator now has been set up to interpret that 45 as a degree measure. And then press the enter key, and you should get a 1, okay? And if you don't get a 1, watch this video again. And if that's not helping, message me, see me in class, meet with me in Zoom, something like that. Or get an older brother, sister, mom, dad to help you put the calculator in degree mode, okay? Tangent of 45 degrees is 1, and that's a quick way of checking that your calculator is really in degree mode. Okay, so now that we've got our calculator set up properly, and trust me, without your calculators, you cannot get the answer to a single one of these questions today, not even close. Okay, so you're absolutely going to need a calculator to do these. All right, so first problem says find, well, you know, before we get to the first problem, I want to tell you one other thing. I want to just comment a little bit on how the calculator knows that the tangent of 45 degrees is 1. Let's go back to how we know that the tangent of 45 degrees is 1. Remember, to find the tangent or sine or cosine of any acute angle measure, you draw a right triangle, you put that acute angle measure in one of the angles there, and then the tangent of that angle, we recall from SOHCAHTOA, would be the opposite side over the adjacent side. And the opposite side from this 45-degree angle is over here. I'm going to call that x. And the adjacent side is down here. Well, if this is a right triangle with a 45-degree angle in it, then this other angle is 45 degrees. And it's not only a right triangle, it's an isosceles right triangle, which means this side down here would have to be the same as this side over here. I mean, whatever they are, they're both the same. They could both be 5, they could both be 10, they could both be 9.8. Whatever they are, they're the same. And so the length of this side divided by itself, basically, is going to be 1. So that's how we know that the tangent is 45 degrees is 1. How does your calculator know that the tangent of 45 degrees is 1? When you push in tangent of 45, does the calculator draw itself a triangle? Does it know anything about isosceles right triangles? What if you put in tangent of 44 degrees? Then what is it? Does it draw itself another triangle? Well, no, the calculator is not in the business of drawing triangles for itself. Okay. And it's not the case either that somebody figured out what all of the answers to tangents and sines and cosines are and sort of programmed them into the calculator so that the calculator just looks them up. That's not what the calculator is doing either. Although about 2,000 years ago, that's what mathematicians did. Somebody figured out a long, grueling way using a lot of geometry and algebra to find out what the sine of 45 degrees and 44 degrees and 43 degrees and every angle down to 1 degree and all the way up to 90. In fact, as of 2,000 years ago, human beings were able to do this to every half a degree, figure out what the sine and the cosine and tangent values are. So for thousands of years, people have relied on tables with these values printed in them. But once calculators were invented, nobody's punched all these numbers into a table. Calculators actually calculate the value of the tangent of 45 degrees on the fly. Every time you ask the calculator for the trig output for any particular input, the calculator actually calculates it on the fly. There's a method that the calculator uses that was not known to men until calculus was invented only about 300 years ago. Okay. And the calculator actually uses that method to find these trig output values. Just, I don't know, thought that might be interesting to you. But anyway, let's go on now to solve some of these problems. We're trying to find the length of QV. The side QV is right here. It might be worth, I don't want black. I want to use a different color. It might be worth highlighting that side that we're looking for. Okay. This is a right triangle, and we do have one side length given to us in this triangle, but only one other side length. If we had both of the other side lengths, we'd be able to use the Pythagorean theorem. But we haven't been given the other two side lengths, just the one. Okay. But do you notice there is a second piece of information given to us about this right triangle? See it? We're given the 28-degree angle measure there, right? Now, if we're using the Pythagorean theorem to find the side lengths, angle measures are of no use to us. We don't need them. And if we're given them, we would just ignore them. Okay? But here we've been given not two sides, but one side and an angle measure. And that angle measure combined with that side length of 75 is going to help us find the other side length. But here's what you've got to do. You've got to notice that angle measure, and you've got to position yourself at the vertex of that angle, just like we were doing in the last lesson to find sine and cosine and tangent output values. Position yourself at the vertex of that acute angle. And then you've got to train yourself to ask yourself, now, which side am I looking for in this triangle? From angle Q's point of view, am I looking for the opposite side from that 28-degree angle, the adjacent side to that 28-degree angle, or am I looking for the hypotenuse of the triangle? Okay. Well, from this 28-degree angle's position in this triangle, the side that we're looking for, QV here, is the adjacent side to that 28-degree angle, right? This over here, VM would be the opposite side. 75 is clearly the hypotenuse. Okay. The opposite side is of no value to us because we don't know its value. Okay. But the hypotenuse is worth something to us because we know its value, and it's going to help us find the adjacent. So now here's the next thing you've got to train yourself to do. You've got to go back to this word. Remember this? We were referring to this dozens of times in the last lesson. And you've got to find in that word the trig function. Is it the sine, or is it the cosine, or is it the tangent that connects adjacent sides and hypotenuses? Which of those three trig functions? Is it the sine, the cosine, or the tangent? Which one of those three connects an adjacent and a hypotenuse? Well, it's this one right here, right? The cosine, the CAH, okay, connects cosine of an angle with the adjacent side and the hypotenuse. So now what you have to learn to do is to say to yourself, well, now I have to write an equation. I have to write a cosine equation because it's the cosine that connects these two sides with the angle. And so we begin writing cosine. Now, every trig function has an input. Okay. What is going to be the input in this equation? Remember, inputs to sine, cosine, and tangent are always acute angle measures. And the only acute angle measure we have in this problem is the 28 degrees. So that is your input to cosine. And then SOHCAHTOA reminds us that the cosine of that angle measure is equal to the adjacent side, which we don't know right now. Let's call it x, divided by the hypotenuse, which we do know is 75. So you got to learn how to generate this equation, like from scratch, okay? And now notice this equation only has one true variable in it, that's the x, although that cosine of 28 degrees might look very, very mysterious to you. But hey, I was just telling you a few minutes ago, the calculator can come up with the output value for the cosine of 28 degrees. It can do it for cosine of 28.5 degrees or 28.8362 degrees or any input value you want. It can come up with the cosine output. So you could right now, don't do this, you could reach for your calculator, punch in cosine of 28, hit the enter button, and you would get some really ugly long decimal value for cosine of 28 degrees. And you could rewrite this equation, putting that decimal value in its place. But the decimal values never stop and they never repeat, okay? And we want to get as precise an answer to this question as we want. And I don't want to have to carry all of those decimal places around. I don't want to have to write them down. I don't want to have to punch them back in my calculator again. So I don't advise reaching for the calculator at this point. What I advise instead is solving this equation for x, because that's what we're after. We're after this x here. And there's only one algebraic step we need to take here to isolate that x. Right now, x is being divided by 75. How do we undo division by 75? We multiply both sides by 75. And that will cancel out the division here. And now's the time to reach for your calculator and punch all of this in your calculator all at once. 75 times. Then hit the cosine button, and then 28, and then close the parenthesis, and then hit your enter key, and you'll get the answer to x all at once or immediately. Now, the problem doesn't say, and you're going to have lots of decimal places in your answer, but I generally like to round answers for all of these trig problems to 1 decimal place. On the quiz that you're going to get, I will be very clear. I'll be very specific as to how many decimal places I want, if any. Maybe I'll ask you to round to the nearest whole number. But for today, I'm going to round all of these to 1 decimal place. So approximately, because I'm rounding here. Okay. Now, if you don't have a TI 80 something or other, what you might need to do, instead of punching in the 75 times, is you might need to punch in cosine of 28 degrees first. You don't need the degree symbol, and hit the enter key, and you'll get that long decimal answer. And then immediately, don't clear the window, immediately then press your times button to tell the calculator you want to multiply that answer by 75. And you should get the same result, 66.2. Okay, that is the length of side QV. And we found it using trigonometry. Okay, not by the Pythagorean theorem, that was not available to us. Okay. Before we race ahead to the next problem, and we've got 5 more problems we're going to work through. So if this all seems to be going a little fast and you're thinking, wait, I'm not really sure I could do that on my own yet, it's all right. We're going to go through a bunch more examples. But first, I want to try to drill this into you also. Anytime you are solving a trigonometry problem, once you get an answer, before you race on to the next problem, and I know, when you're trying to solve a problem and you get an answer, you're so happy that you got the answer. The tendency is to just circle it and zip on to the next problem. Okay? Try to learn in this unit that anytime you get an answer to a trig problem, to check back in the picture to see if the answer makes sense, because there are many times where students make mistakes and they get answers that they haven't even taken the time to consider that their answers make no sense at all. You can tell sometimes when an answer that you've gotten makes no sense at all. And I'm going to tell you how you can tell. The answer we got in this case was 66.2. I'm going to give you an answer for the length of that side that absolutely makes no sense at all. Okay? Suppose you had punched a bunch of things in your calculator and you came up with an answer of 76.2. Okay, let me erase some stuff here, clean up this picture. Let's imagine that you had typed a bunch of stuff in your calculator and you came up with an answer of not 66.2, but 76.2 for the length of QV. There's no way on earth could QV be 76.2 in this triangle. Do you know why? Look at the triangle. Look at the other sides in the triangle. You see the one other side that we know something about? We've been told that the hypotenuse is 75, right? The hypotenuse is always the longest side in the triangle, right? So QV cannot possibly be more than 75. It's got to be less than 75. You get anything bigger than 75, you know you made a mistake, okay? And if you get an answer like 0.46, 0.46, well, that's not an impossible length for the side of a triangle. But really, if this hypotenuse is 75 units long, let's call them centimeters, 75 centimeters long, do you suppose this side of the triangle is less than 1 centimeter long? Yeah, I don't think so, okay? I mean, a triangle side could be less than 1 centimeter long. And look, here's a triangle, a right triangle where, and there's the right angle down there. If this hypotenuse is 50 centimeters, that really super short side down there could be really, really small, right? But then this would be a super, super skinny angle up there. I mean, it's not likely that you're going to come up with side lengths that are less than 1 unit long. Okay. I mean, I could make up problems like that, but I'm just not going to. Okay. So every time you get an answer, check back in the picture to make sure the answer seems reasonable. Okay. And what's reasonable are legs that are shorter than the hypotenuse. Or if you're trying to find the hypotenuse, the answer you get better be longer than one of the legs. That's mostly what you're looking for here to check on the reasonableness of your answer. Okay. And quite honestly, it is possible for you to get an incorrect answer and for that answer to still seem reasonable. And so you might not catch yourself making a mistake. I mean, we could have come up with an answer for this of, let's say, 57.8. That's less than 75, so that's good. It doesn't really look like that's off or crazy wrong. Okay, so it's possible for you to get a wrong answer and not catch it, but there's really no excuse for getting an impossibly wrong answer and not catching it and trying to fix it. Okay. Go on to number 2. This problem's not much different in most of the new stuff that we're having to learn here. The algebra at the end is a little bit different. The algebra is going to be a little bit more involved. Okay. But what do I like to do again? I like to highlight the segment that we're trying to find, PB, and I like to highlight the other segment that we've been given that's going to help us find the one that's missing. Okay, and I like to invent a variable for the one that's missing. And then you've got to notice the acute angle that's been given to you right here, 25 degrees. And you have to ask yourself, opposite, adjacent, or hypotenuse? What side are we looking for here? This X. What side is it from that 25-degree angle's point of view? It is the adjacent side, right? This is the adjacent side. Much like it was over here, it was the adjacent side. But what side have we been given? This time we've been given the opposite side. So then you go back to SOHCAHTOA and you look for which of these 3 functions connects opposite O and adjacent A. Well, it's the tangent right there, right? Tangent is opposite over adjacent. So now we've got to write a tangent equation. It begins with tangent, which is a function which requires an input, and the input is always an angle measure, and the only acute angle measure we have in this diagram is the 25 degrees. Okay. That's equal to the opposite. Now this time the opposite is known to us. It's 36. Over the adjacent, right? The order of these letters matters. Tangent is opposite over adjacent, and the adjacent is the unknown this time. Okay. Now again, I could punch tangent of 25 degrees in the calculator and get some really long, ugly decimal place that I would have to write down, and it's a pain, and I don't want to do it. I want to solve this equation for X right now, but the algebra here is a little bit more involved. And I believe we ran into this when we were doing similarity problems, so this should not be new. Certainly you learned, I hope you learned how to do this in algebra, but definitely we went through this when we were doing similar triangle work. This X is in the denominator of the fraction, okay? And that makes it a little bit trickier to deal with. You do not want to divide both sides by 36. That's not going to solve this for X. You don't want to multiply both sides by 36 or do any one thing that you think is going to solve this for X. Okay? The first thing you have to do is get the X out of that denominator. Okay? Because we don't ultimately want to solve for, let's say, 1 over X. We don't want to have an equation where the X is in the denominator and telling us that something over X is equal to 5. Well, that's not what we're looking for. We want to know what the actual X value is, not 1 over the X value or 2 over the X value or anything over the X value. Okay. And if we divide both sides by 36, we're going to be stuck with a 1 over x on the right-hand side. So we got to get that x out of the denominator. And the way you get it out of the denominator is to multiply both sides by x. Okay? Which again is not a step that, we take a lot in algebra and solving our problems. It's not something you're used to doing a lot of. We did some of it back in similar triangles, so I hope it rings a bell. Okay. Multiplying both sides by a variable. That's a little bit unusual, but not unheard of for you. And that will cancel out the x's over here. And now we have remaining an equation that has no fraction in it anywhere. But now the x is still not isolated. Okay. It is being multiplied by the tangent of 25 degrees. X times the tangent of 25 degrees. I'm just recopying this equation that results from multiplying both sides by x. We're still trying to isolate the x, and right now the x is being multiplied by tangent of 25 degrees, and we want to isolate that x. So how do we undo multiplication? With division. We want to divide this side by this whole function expression, the tangent of 25 degrees. And this side by the tangent of 25 degrees. Okay? Pay careful attention to that. We're not dividing both sides by 25. And we're not dividing both sides by just the word tangent, like with no input value. Okay? We need to divide by that whole expression, tangent of 25 degrees. That'll cancel out the multiplication. And now this can all be put in your calculator. If you've got a graphing calculator, you can put it in just like that. You can put in 36 divided by tangent of 25, close parenthesis. Okay. And the calculator will do the tangent of 25 degrees. First, it'll get a value, and then it'll divide the 36 by that value, and it will tell you that the value of x in this case turns out to be, got to check my notes, about 77.2. Okay. If you're not carrying around a graphing calculator, you might need to do this tangent of 25 first, get a decimal value, keep track of that decimal value, all the decimal places, and then divide 36 by that decimal value. Okay. Now, let's check and see if 77.2 seems reasonable in this picture. Okay. Oh my gosh, I was erasing things and my eraser just stopped right in the middle. 77.2. And what side did we find? PB, 77.2. Compare that to the other side in the triangle. The other side is 36. Okay. Now, that side BP looks like it should be longer than 36, but does it have to be longer than 36? It's not the hypotenuse. 77.2 is not the hypotenuse. I mean, it really is the case that either leg of a right triangle could be longer than the other, right? And we learned way back at the beginning of the year not to trust our visual reflexes just because BP looks longer than the 36. Does that really mean it has to be longer to the 36? Well, there is another clue in this problem that, BP must be longer than the 36. And that's the fact that this angle right here is 25 degrees. If this is a right triangle and that angle is 25 degrees, then this angle up here, you could figure this out quickly and easily, would have to be 65 degrees. Subtract the 90 and the 25 from 180, and you'll get 65, right? So this side being across from a 65 degree angle is going to be larger than a side which is across from a 25 degree angle. Okay? Larger angles create larger sides across from them. Look at it this way. Suppose I've got two sides of a triangle right here, and the third side is formed by connecting the endpoints of these two sides. And how large is this angle here? I don't know, about 30 degrees, whatever, right? the wider I make this angle down here, you see this, the larger and larger the side across from that angle gets, it grows larger and larger. The wider I make that angle, the longer the side across from that angle is going to be. And so larger sides are always across from larger angles. Okay. And so anything less than 45 degrees in a right triangle, that side's going to be the smaller side. The side across from an angle which is less than 45 is always going to be smaller than the side on the triangle which is across from an angle which is more than 45 degrees. And if both angles are 45 degrees, well, we already know then both of the sides are the same. So there is a way of knowing that, yeah, BP has to be larger than the 36. And so if we get anything that's less than 36, we know that that's wrong, okay? Now, one more thing I want to tell you, just to put you at ease, is I am never going to intentionally draw triangle pictures to try to fool you, okay? I would not have drawn this triangle like this and made this angle 25 degrees down there. That does not look like a 25-degree angle. That looks larger than 45, doesn't it? And made this 36, and then asked you to solve for this side where you come up with 77.2, and then you're scratching your head going, wait a minute, that side looks pretty short. It looks a lot shorter than that 36. I think I did something wrong. I mean, that would just be mean, okay? I'm not going to do that to you, okay? So you can, to a certain extent, rely on your visual judgment, but be careful. We always want to be careful, okay? All right, let's move on and do two more problems like these, and we're going to work through these somewhat quickly, and then we have something new to learn in problems 5 and 6. So find the length of TR. TR is here, and the side that we know something about that's going to help us find TR is this side here, TZ. And you've got to notice the acute angle, 49 degrees. Okay. Oh, hey, wait, before we go to solve this problem, let's just see here. See, 49 degrees is larger than 45. So this angle over here must be less than 45. So this side, this leg of the triangle, would definitely have to be longer than the other leg of the triangle. And it looks like it's longer than the other leg, right? But in the end, we better make sure that we come out with a length for this leg of the triangle that is less than 54, right? If we come out with anything bigger than 54, we know we made a mistake. Well, from the 49-degree angle's point of view, this side is the opposite side, and this side is the hypotenuse. You go back to SOHCAHTOA, what connects opposite and hypotenuse? It's the sine function. So you must write a sine equation. And the input to sine is the degree measure, 49 degrees, and the sine of an angle is the opposite, which currently we don't know. I'm just going to call it opposite, over the hypotenuse, which we do know is 54. To solve that, before you reach for the calculator, right, we're trying to isolate that opposite side, multiply both sides by 54. That's all we need to do to isolate this opposite variable. Now we can pick up the calculator, punch all of that in all at once, and we find out that the opposite side is equal to, checking my notes, 40.8. Wait, does that seem reasonable? Well, it's less than the hypotenuse, okay, and 40.8 seems reasonable to me. Number 4, if we were in class, I'd probably ask you to do this on your own, okay, and maybe you can stop the video and try this now if you want, but there's plenty of homework problems to practice this on. We're trying to find the length of KC, that's here. Here's the side we know that's going to help us. Here's the acute angle that we know. From that acute angle's point of view, this is the adjacent side. This is the hypotenuse. Okay. What connects adjacent and hypotenuse? SOHCAHTOA. SOHCAHTOA. So it's the cosine. Okay. So write your cosine equation. The input is the angle measure. Cosine of 26 degrees equals the adjacent, which we know, over the hypotenuse. I'm going to call the hypotenuse H, which we don't know. Oh, here's this algebra trouble again. Okay. It's going to take 2 algebraic steps to isolate that h properly. We start by multiplying both sides by h. Okay. And that produces this equation. H times the cosine of 36 degrees equals 87. And then divide both sides by the cosine of 36, because that will cancel out the multiplication right here. That multiplication gets canceled out. Now reach for your calculator, punch all of that in, and we get that h is equal to, my calculation earlier told me 96.8. Does that seem reasonable for the length of KC? Well, KC is the hypotenuse. It better be the longest side in the triangle. And we had a leg of 87, so I'm feeling pretty good about that. Okay. Last 2 problems. No pictures drawn here. Guess what we're going to have to do? Draw pictures of right triangles. Okay. But there are key phrases in each of these word problems that you want to identify before you go right drawing the triangles. Okay. In the first problem, the key phrase is angle of elevation. Okay. And in the other problem, we see this phrase angle of depression. You got to know what these phrases mean. Okay. So in the completed notes, if you go look at my completed notes, what's posted down in the bottom, I'm not going to write this out, is that an angle of elevation and an angle of depression, by definition, I mean, here's just what these things mean. They're always an angle where one of the 2 sides of the angle is a horizontal line. Must be a horizontal line. If you don't have a horizontal line in your picture, you don't have an angle of elevation or an angle of depression. Okay. So when I see that phrase angle of elevation, I immediately draw a right triangle starting with a horizontal line. And then that's going to be one leg of the triangle, and the other leg is going to go upwards. The word elevation, when you ride an elevator, you can go up or down, I guess. But if you elevate something, if we just talk about, well, let's elevate this, we usually mean let's make it go up. Let's go up with it. So draw the horizontal line. That's one leg of your triangle. Then draw a vertical segment for the other going up, not down. We could make a right angle going down, but make it go up. Okay. And it really doesn't matter how long either one of those legs are, but then put your hypotenuse in connecting them. Now, there's only one acute angle in this triangle that's made with a horizontal line, right? There's 2 acute angles in this picture. There's one down here and there's one up there. Both of those are acute angles. But the only acute angle made with the horizontal line is that angle in the lower left corner. That's the angle that we're being told is 55 degrees. Okay. I like to get my triangle drawn correctly and the angle placed properly before I put anything else in the picture. Okay. So what else is the problem telling us about? A girl flies a kite at the end of a 200-foot string. If the angle of elevation, watch this now. Here's a couple of other key phrases. From the girl to the kite is 55 degrees. Okay. How high is the kite above the ground? So these phrases, from the girl to the kite, and if you just think about what the problem is describing for us, where in this picture would you place the girl? Where would you place the kite? Where would you place the 200-foot string? Okay. Well, you've flown kites, or you've seen people flying kites, or you've seen pictures or videos of people flying kites. Somebody's standing on the ground. The kite is up in the sky. The string is usually at some kind of an angle. It's not usually going straight up in the air or straight along the ground unless the kite has fallen down. So here's the string. Okay. The string is one of the sides of the triangle. Okay. And we've got to use our imagination here that the girl is really just this point down here. Okay. The girl is not one of the sides of the triangle. And the kite also is just this point up here. The kite is up in the sky. It's this point up in the sky. The girl is this point down on the ground. And there's this really long 200-foot string connecting the girl to the kite. And this 55-degree angle of elevation is going up from the girl. It's an upward angle from the girl's point of view towards the kite in the sky. Okay. And what are we being asked? We're being asked, how high is the kite above the ground? Where's that in our picture? What are we looking for in the picture? We're looking for how high is this kite above the ground right here? What is this distance? That's what we're looking for. We're looking for that height. I'm going to put an H for height. Let's not confuse that with H for hypotenuse. Okay. You can call it any variable you want. Call it X, call it Y. Okay. But you got to set up this whole picture properly. And then do what we did in the previous 4 problems. Figure out, okay, which side is this, the one we're given, and the one we're looking for from this angle's point of view. Well, from the 55-degree angle point of view, whoops, I don't want that. I want to go back to a pen. This side is the opposite. This side is the hypotenuse. Okay, so maybe I better change that H. I don't want to confuse that with hypotenuse. Let's call that Y because it's a length in the vertical direction. Okay, you could call it X too. That wouldn't matter. But both are probably better than H. All right, opposite and hypotenuse are connected by sine. So sine of 55 degrees is equal to the opposite, which we don't know, over the hypotenuse, which we do know. Multiply both sides by 200 to isolate the Y. And then pick up your calculator and put all that in. And my result from earlier told me 163.8. So the kite is 163.8 feet high. Does that seem reasonable? Well, it's got to be less than 200. We know that because 200 is the hypotenuse. Now, does that look like 163.8 compared to that 200? I don't know. That Y looks pretty short. You know what the problem is? Problem is that angle doesn't really look like a 55-degree angle, right? Doesn't that angle look less than 45 degrees? That's why we're possibly getting fooled here, right? If we'd actually drawn a better picture, a 55-degree angle would have been something like that. And the hypotenuse is 200. And then 163.8 would look a little more reasonable here. Okay. So we did not get the wrong answer. We don't want to fool ourselves into thinking we got the wrong answer. It's just that we drew a picture that could have been better at the start. Right? All right, last problem. Angle of depression. Whenever I see the phrase angle of elevation or angle of depression, I start drawing a right triangle with a horizontal line. But when you're depressed, you are feeling down, right? You see angle of depression, think down. And so after drawing that horizontal line, I'm going to draw a right angle that goes down instead of up for elevation. And then I'm going to connect the ends of those 2 legs of the triangle. And I'm going to put my angle of depression, which I'm told is 24 degrees right there, because that's the acute angle with the horizontal side in it. Here's another acute angle down there, but that's got a vertical side in it. Okay, not a horizontal. So 24 degrees goes there, and that really looks like a 24-degree angle, so that's good. Okay. Now, what else goes elsewhere? We got a pilot of a plane flying at an altitude of 600 feet, and he sees his target landing point off in the distance. We got a plane in the air. We got a landing point off in the distance. The landing point is not in the air, right? The landing point is on the ground. We got a plane in the air. We got a point on the ground where the plane is trying to land. Okay. And the plane is at a altitude of 600 feet. Okay, now you know how altitudes and planes are measured. They're measured straight up and down. Okay, so it seems like the only place for this 600 feet to go is right here. Okay, but be careful. The temptation here would be to put the plane right up here at the top of the right angle, but no, the plane is over here, and it is aiming for this landing point over here on the ground. The plane is not directly above the landing point. See, it says the pilot sees his target landing point off in the distance. He's not directly above it looking straight down on it. It's off in the distance. So here is the pilot in the plane. It's this little dot in our picture. It's not a segment. Okay. The 600 feet, that length is a segment. That distance is a segment. In these sorts of problems, you will be given lengths, and those lengths go along the sides of the triangle, a side of the triangle somewhere. But all the objects, most of the objects, really are represented just by points in the triangle. Okay. Now, that's not exactly true with this kite problem because the string was that whole segment there, right? But here, the plane is a point, the landing point is a point, okay? And what is the question asking us? How far away from a point on the ground directly below the plane is the landing point? So we've got to find a point on the ground which is directly beneath the plane. That point right there. How far is that point, let's call it A, from the landing point? What is that distance right there? That's what we're being asked to find. Okay. Now, you may notice that what we've created here is not just a triangle, but a rectangle. And so I could put that X up here also. If I solve for that X, it's going to be the same as the X that I'm being asked about. And the X up top actually belongs to the triangle that I've created. So that's a more useful place to put the X. Okay. This can be tricky, setting up these angle of depression problems. So the angle of depression problems are always have a tendency to be trickier than angle of elevation problems. Okay. But now that we've got it set up properly, what is the trig? We're looking for this side. We know this side. We know this angle. From this angle's point of view, 600 is the opposite. The X is the adjacent. Tangent is what connects opposite and adjacent. Tangent of 24 degrees equals the opposite, which is 600, divided by the adjacent, which we don't know. Oh, there's that Payne algebra again. Multiply both sides by X to bring X up to the numerator level, and then divide both sides of the equation by the tangent of 24 degrees, which will cancel out there. And so X equals 600 divided by the tangent of 24 degrees, which my calculator told me earlier, X is equal to 1,347.6 feet, which in my picture, I'd say looks pretty reasonable. Right? If this is 600 feet, and that's a fairly small 24-degree angle, that's a larger than 24-degree angle. That segment's got to be longer than 600. 1,347 feet seems reasonable. Okay. That's it. You're not going to see anything in the homework that you didn't see in these notes. If you need to replay some of this video to see how to do a problem in order to do one, that might be worthwhile. Okay, good luck.